Before considering the process of ionic bonding specifically, it's worth remembering that chemical processes are likely to result in elements following the octet rule. And this is a general rule that states that atoms tend to gain a valence shell with 8 electrons after a process has been completed. We'll come and visit this again shortly. So let's consider the start point for ionic bonding. In order to form an ionic bond, we're really looking for two elements with a large difference in electronegativity. And as a general rule, we're looking for a difference of approximately 1.8 or greater in order to find significant ionic character in my bonding. And because we're looking for two elements with large differences in electronegativity, we're often talking about a metal and non-metal element. And why is that? Well, if I look at the Pauling electronegativity values in the data booklet, I can see that the metals on the left-hand side tend to have quite low electronegativity values, whereas the non-metals on the right tend to have high electronegativity values. So let's consider the formation of an ionic bond between sodium and chlorine. So when considering the reaction between sodium and chlorine, we should also remember that we're actually dealing with a large number of both atoms in a lump of sodium metal and in chlorine gas. But in order to simplify this example, we're going to take a start point of just a single atom of sodium. And you can see here on my sodium I've represented the 1 electron in its valence energy level and 1 atom of chlorine. Again, in this Lewis diagram, I've shown the 7 electrons in the valence energy level of a chlorine atom. Given that the electronegativity value for sodium is 0.9 and the electronegativity value for chlorine is 3, it's clear to see that chlorine is significantly more electronegative and therefore will pull on valence electrons more strongly. And in the formation of an ionic bond, the chlorine is actually electronegative enough to pull that electron from sodium completely away from the sodium and take it for itself. So we'll now end up with a sodium that's lost 1 electron, so has become a positive ion, and then a chlorine that has gained 1 electron, so has therefore become a negative chloride ion. What you'll notice here is that now my sodium ion and chloride ion both complete the octet rule that we talked about at the beginning. The sodium atom lost its outer electron, so its valence energy level is now actually the second energy level, which is full with 8 electrons. And the chlorine atom that gained 1 electron now has 8 valence electrons, as you can see in the Lewis diagram. Importantly, the resulting system that I've produced is now also very stable, and that's because I've produced 2 oppositely charged ions, and these 2 ions will electrostatically attract each other in what we call an ionic bond. So technically the ionic bond is the electrostatic attraction between oppositely charged ions. And the key part of this definition is the electrostatic attraction. When defining any type of bonding, we're always looking to consider what type of electrostatic attraction is occurring. Because in this example, only 1 of each ion is required in order to complete the octet rule, in both cases, we write an ionic formula for this compound, NaCl. And this formula should always show the correct ratio of each ion required to complete the octet rule. The name here would be sodium chloride. However, we're missing one important feature of ionic bonding. In reality, we start this process with many atoms of each element. So during the process, we actually form many oppositely charged ions. And if I consider the most stable arrangement of many oppositely charged ions, I might predict that they end up something like this. Here we can see a nice 3D lattice structure where the ions are arranged in an alternating fashion. And this means that instead of just 1 positive ion being attracted to 1 negative ion, each ion is actually attracted to several oppositely charged ions in the lattice. This is sometimes considered a form of non-directional bonding, because attractions are occurring in lots of different directions. And we can find some evidence of these 3D lattice structures if I, for example, look down a microscope at some salt crystals. You'll notice that similar to the 3D diagram before, these salt crystals tend to have regular cubic-shaped structures. And this is just one piece of evidence that supports our thinking here. Let's now summarize the key points from this video. So the formation of an ionic bond occurs between elements with large differences in electronegativity, which are often metals and nonmetals. The more electronegative element is able to attract and actually remove an electron from the other element. And this means that the octet rule is achieved by the formation of ions. An ionic bond is simply the electrostatic attraction between oppositely charged ions. And finally, these ionic substances, because they are made from many oppositely charged ions, are actually lattice structures and never found as a single pair of ions. And that's pretty much it. Hopefully, this video is of some help.